Let's continue with Ksp problems. It says calculate the Ksp value for bismuth sulfide Bi2S3, which has a solubility of 1.0 times 10 to the 15th moles per liter at 25 degrees C. Let's start with what this looks like in terms of an equation. Bi2S3 is a solid, and when it dissolves, it forms 2 bismuth ions and 3 sulfide ions. We don't really know, nor do we care how much of the BiS3 that we have. We know that the solvent has no ions. We also know that the Ksp expression will only include the aqueous ions, and that would be the Bi3 raised to the 2nd power and the sulfide ion raised to the 3rd power. So this is our initial conditions. The change that will happen to reach equilibrium as this dissolves to a small extent, because it has very small Ksp, is for every 1 mole of Bi2S3 that dissolves, 2 moles of the ions, the bismuth ions, will be formed, and 3 moles of the sulfide ions will be formed. Now they said that this bismuth sulfide has a solubility, which would be this value right here at 25 degrees C. So we know that this is the value of X, and that at equilibrium the bismuth ion concentration will be 2 times this value of X, or 2 times 10 to the negative 15th, and the sulfide ion concentration will be 3 times this value of X, or 3.0 times 10 to the negative 15th. So we can find the Ksp value by substituting into this expression, where the bismuth ion concentration, molar concentration, or molarity, is this value raised to the 2nd power, and the sulfide ion concentration is this value raised to the 3rd power. And when we do our math, we find that the Ksp from bismuth sulfide is a very, very small value, 1.1 times 10 to the negative 73rd. It really doesn't dissolve. You will recall earlier in your study of equilibrium that you could tell the strength of an acid or a base just by looking at the value of the Ka or Kb value. The higher the number, the stronger the acid or base. Well, we can sort of rank solubility the same way. The larger the number, the more soluble, with this important caveat. They must disintegrate or dissolve into the same number of ions. In this case, the Ksp expression for all of these will be the cation raised to the 1st power times the anion raised to the 1st power. So the Ksp expression is going to be K squared is equal to Ksp. So we could very easily look at these and rank them. This is the largest number, and this one, and this one. So this would be more soluble than this, than that. What would happen if the Ksp value was not an equal split between the cations? You would have to do a Rice table. Let's just say that you had something like this, and you would have to find the value of X and then figure out the Ksp. That ranks the solubility that way. All right. Let's talk about some factors that affect solubility. This is an equilibrium expression, so a common ion will affect the solubility according to Le Chatelier's principle. If you have let's say, this particular equilibrium expression, and it is at equilibrium, if you add a common ion, it will shift equilibrium to the left, and that will make less of the calcium fluoride dissolve. How much less? Well, let's figure this out right now. To find the solubility of CaF2, whose Ks value at 25 degrees C is 4 times 10 to the negative 11, that has in the solvent some NaF. So we start out with some amount of calcium fluoride. Initially, we have no calcium ions in our solution, but we do have some fluoride ions. If the sodium fluoride is totally, because it's group 1 cation, totally soluble, so it will yield 0.25 molar sodium ions and 0.025 molar fluoride ions. That will be the common ion in this expression. So we start with these values. The change that will occur for every one of these that dissolves, you have one of these and 2 fluoride ions. So the molar solubility at equilibrium of calcium fluoride is X. The molar concentration of the calcium ions will be X, and the molar concentration of the fluoride ions will be 0.025 plus 2X. Right, our Ksp expression is equal to the calcium ion concentration times the fluoride ion concentration raised to the second power. Our Ksp value is 4.0 times 10 to the negative 11, which is a very small number. Let's recall in our previous K math portion, we were allowed to drop the X in certain cases. And the certain case is when you have a very small K value, and the only time that you can drop the X is when the value is very small compared to the starting value. And this will be the case now. So we can disregard this 2X. When we do this math, X, our molar solubility of calcium fluoride, is 6.4 times 10 to the negative 8th molar. And in our Ksp work, we have learned that we generally say moles